In this video, we are going to talk about multiple representations of functions, and our goal is to be able to create and analyze multiple representations in the context of a situation. In this video, we're going to focus on the creating piece of it. So let's take a look at our first example. We are given a situation in this example. Mr. Goldwasser and Mr. Saxton are planning the homecoming dance and need to order the correct number of tables. The tables are hexagon shaped and 6 chairs will be placed around each table. We are being asked to create different representations for this situation. They would like us to create a table of values, a graph, and write an algebraic rule. So we are given this picture to kind of help us determine what's going on. And anytime we do these representations in math, we're trying to look for patterns. So if I have one table, I have 6 seats. At the next table, I have 6 more seats. So now I have a total of 12. At the next table, I have 6 more seats. So now I have a total of 18. That repeated pattern is we are just adding 6 more seats every single time we add another table. So I can take that information now and go ahead and create a table of values to represent that. So for 0 tables, I have 0 seats. For 1, I have 6. 2, I have 12. 3, I have 18. And 4 tables, I have 24 seats. As you can see, we just added 6 each time as we stated in the pattern. We'll come back to this process piece in a second. Now we're going to go ahead and take this table and create a graph of the information. I'm going to go ahead and label these axes. I went ahead and made the y-axis go by 6's since that's what we're counting by. So if I take this information and go ahead and plot the points, at 0 tables there were 0 seats. For 1 there was 6. 2, 12, 3, 18, and 4, 24. So this is all the information that was in our table, but I can continue this pattern to create a graph that would represent more tables than what is shown in my table. So now we have this graph. Next, they want us to create an algebraic rule, and that's where this process column of our table comes really into play and becomes very helpful. So let's think about what our variables represent. Well, we know we're showing the relationship between the number of tables and the number of seats. So our independent variable, number of tables, we are going to use a variable to represent that. So I'm going to use x. You can use anything you want though. Our dependent variable is the number of seats. I'm going to go ahead and use y. So essentially, I need to show the relationship between y and x. So if I look at my table, this is how I find it to be the most helpful. In other words, how did I start at 0 and get to 0? 1 and get to 6, 2 and get to 12. That's our goal that we're trying to find. Well, if I look at this, it looks like I did, to get 0, I did 6 people, or seats, times 0 tables. For the next one, I did 6 people times 1 table, 6 people times 2 tables, and so on and so on and so on. So we can see that in our rule, this thing that stays the same every time that's part of it is always this 6 piece. So that's going to be part of my rule. So we know that y is equal to 6 times, and then we're looking at something. So I need to figure out what that something is. So I can see that this 0 matches this 0, and this 1 matches this 1. So I'm taking 6 times the number of tables. Well, we used a variable to represent number of tables. We used the variable x. So our rule would be y equals 6 times x. So now we've created 3 different representations, all to represent the same situation. We have a graph, we have a table, and we have an algebraic rule. So we want to use those representations now to answer some questions. So what is the y-intercept of the graph, and what does this point mean in the context of the situation? Well, we know a y-intercept is the point of which our graph crosses the y-axis. We can see that happens at the point 0, 0. Knowing what our variables represent, that 0.00 then means that for 0 tables, there are 0 seats. Now we are being asked to use our rule, so y equals 6 times x, to determine how many people can be seated at 22 tables, because 22 is not shown in my graph and it's not shown in my table. So I'm going to take 22 and substitute it in the rule where it belongs. Since number of tables represents x, then in the x spot I substituted a 22 and we end up with 132 people. If 650 students have tickets, how many tables do we need? So I'm looking for 650 people, or number of seats, of my y. I don't see that on my graph, and I don't see that in my table. So it looks like we're going to have to use our rule. So again, because 650 represents y, we're going to substitute that in the y spot. After solving, we end up with 108.3. Well, I can't have 0.3 of a table, so we would really need 109 tables. So can this situation have an input of 4.5? Well, our inputs represent the number of tables. It's not possible to have half of a table, so the answer would be no.